Sorry for the late start. Listen, we're going to do a little bit in Chapter 8 today, and I'll tell you exactly what to expect for the test. But it's a lot like what you did in lab. Many of you have done the lab with the meter stick, right, and hanging the weights on it. You know what I'm talking about? That lab? I think everybody that's in lab has done that. But I'll show you what to expect for the exam. But in short, you're going to have to show objects in equilibrium, in rotational equilibrium. Like with the meter stick, you have to figure out what one mass on one side would cause it to be in equilibrium with the other side. We'll do some problems like that. And then also be able to figure out what is the net torque that's acting on an object, whether it's in equilibrium or not. Okay? So those are the only two things that we'll see on this exam, which will be on Wednesday. On Monday, we'll have a review session. So I'll just set aside Monday as a review because we have a lot of business going on with chapters 5, 6, 7, and then there's a little bit of chapter 8. Okay? You doing okay today? Had a good weekend? Yeah? Okay. Today is? Have a good weekend. No, we didn't have a weekend yet, have we? No, tomorrow is the weekend. Yeah. You have a good weekend planned, I guess. Yes? With lots of exciting things, like sleep and studying. These are so cool. So anyway, we will have a review on Monday. We might have a help session. Y'all want a help session on Tuesday? Okay, I'll schedule one soon. I'll send an email out. Now also, beginning on Monday, we'll start the food drive. Listen, in the food parish and Terrebonne and St. Mary, there are a lot of people that just don't have enough food. Some of those are children, some of those are elderly, and some of those are people that just, they can't find work for whatever reason. And you guys, I know you might not feel like you're privileged, but you really are. Like, you're very wealthy to even be here. I know that you might not feel that way, but that you have resources to allow you to go into college, and that should be really, you should be really grateful for that. And one of the things I think that when we are in places of privilege is that we can help others that might not have the same resources that we have. And that's why we do this food drive at Nichols, to help the community and to help those in need. So what I'm asking, I don't usually do this, I don't usually have stuff that's not part of the course, the extra credit, but I do it for this because I think it's important. What I'm asking is that everybody bring 3 to 5 items. And then, as a class, I'll set some goal. I don't know. I think I have about 150 students. So if I have 150 students, I would say, let's say 600 items. And when we reach 600 items, then I'll give everybody 10 extra credit points. I don't require you to do this because I don't feel like I can really require you to do it. But I do encourage you to do so. And if you bring more than 3 to 5 items, that's fine, slap on the back. Or a pat on the back. Not a slap, a pat on the back. And I'm glad for that. If you choose not to do it, hey, that's okay. But let's work together in order to get 600, let's say, items to give to the food bank. Last year, Nichols, every year we sort of have 7,000 as our goal. That's about 1 per person. But we usually get 10 to 20,000 items that we give to the local food banks. We've become one of their biggest donors. So everybody, we're going to participate in this. You can begin bringing items on Monday. Go home and look through your pantry. If you have things that you don't need or you don't want, that's unexpired, it's still within the expiration date, then please bring them. Or, just pick up a couple extra things at the grocery store. Please do not bring water there. They don't really need water at the food banks because, people drink water out of the tap, except to make formula for babies. So no water. Last year we got too much water. Okay? You can also bring non-food items. Non-food items are really needed. Things like toothpaste, toothbrushes, soap, stuff like that. Because you can't buy that stuff with, what they used to call food stamps, the EBT or whatever. Okay? Michelle? To the front of the class? Oh, just bring it to my office. So bring it to my office, but make sure it comes to me. There will be a box there, but give it directly to me. Okay? Any other questions about that? I'm not requiring it, but I'm encouraging us to participate in this because I think it's worthwhile. Okie dokie? All right, I'll keep you updated on how many items we have, but I do expect that we'll get the full 600. Are there any other questions about whatever? There's a quiz due, I think, Monday, did I make it due? Yeah, Monday, the day before the exam. I might put one more short quiz on there with just like 2 or 3 questions, well, about 4 or 5 questions, to help you practice these network problems. Okay? If I do that, I'll do it today, and I'll send a notice out. Questions, y'all? All right, let's look at this torque stuff, and then we might have a short time just to remind you what to study over the weekend if you do find yourself studying. Okay, so first of all, did we finish the concept test for Chapter 7? I think we did. We did. Okay, so good. Let's begin on Chapter 8. Chapter 8, you're going to see a lot in Chapter 8 for the exam 4. You'll see energy, momentum, Newton's second law, basically everything that we've done from chapters 4, 5, and 6. But in this test, we're just going to see the basics of torques. What is torque? What does it cause? Why is it useful to describe torques? Okay, so Newton's second law extends to rotational motion. Just like forces cause acceleration. Remember we had F equals ma, Newton's second law. Torques will also cause angular acceleration. This will be called alpha. And so later we'll actually develop an expression for Newton's second law that has to do with torques and not forces. That'll be very similar to F equals ma. You can think of torque as an angular force. Right, because we had angular displacement, angular velocity, angular acceleration, and now we can think of torques as an angular force. That's not really its technical name, but we can think of it as an angular force. The magnitude of the torque, say I have a wrench like this, I apply a certain force to it. That force is applied at a certain angle and at a certain radius, r. The magnitude of that torque, we're going to call it the Greek letter, this is tau, the Greek letter tau. The torque will be equal to F times R times the component of R, or rather, let's rewrite this, the component of the force that is perpendicular to the moment arm. So R is the moment arm. We call it the moment arm, but it's really just the distance from where the force is applied to where the axis of rotation is. So you can just call it a radius too if you want. It's the distance from axis of rotation to the applied force. So for example, if I had another force, say right here, the moment arm would be this distance. And y'all saw that in the lab. You put the masses at different points on the meter stick, and then you figured out what was the moment arm. So the torque is equal to the force that is perpendicular, the perpendicular component, of the force to the moment arm. So in this case, I have a force right here. Is it perpendicular to the moment arm? Yes or no? It's not. It's at an angle that's less than 90 degrees. So when I calculate the force, I want to know what is this perpendicular component. Now, I have this angle theta. What am I going to multiply this force by in order to get the perpendicular component? I'm going to do the sine of theta because I want the opposite side, the angle theta. So I can get a more general view of this, that torque is equal to Fr sine theta. And this is on your equation sheet. Fr sine theta. And when theta is equal to 90, then sine of 90 is 1. It just simplifies to this. So when the angle between F and R is 90 degrees, then the torque is just equal to F times R. You will see somewhere the force is not at 90 degrees to the moment arm. We'll work through a couple examples. There's one in the homework as well. The SI unit for torque is a Newton meter. Now, if you remember, newtons for forces, meters for the length of the moment arm. If you recall, back in chapter 5, we said that the units for work are sometimes also Newton meters. You might not remember because I said we're not going to use that unit. That's a different unit from what we have here. Even though it looks the same, it's really measuring something different. So if you've kept that in your mind that work is also Newton meters, just know that work and torques are different quantities. They're different physical quantities. Let's see, clockwise torques are negative. Counterclockwise torques are positive. We've been going along that way, right, because of our unit circle. Our unit circle goes in this direction, which is counterclockwise and positive. Right, it goes 0, 90, 180, 270. It goes in a counterclockwise direction, and so we will too. And in order to have static or equilibrium conditions, what this means here is that alpha will equal to 0. Gosh, what is alpha? We had theta, omega, and alpha measured the what? The acceleration, right? So just like before in chapter 4, I think, yeah, chapter 4, we call it equilibrium to have 0 acceleration. We'll have the same here. So when I have these equilibrium conditions, that is when alpha is equal to 0, I have to have these conditions be met. I have to know that the sum of the torques is equal to 0, and the sum of the forces is equal to 0. Now we saw this in chapter 4, but in this chapter we're going to see this, and we'll look at rotational equilibrium where the sum of the torques is equal to 0. All right, that's sort of a lot of words, but in short, for now, this stuff is going to come back. But for now, we need to know how to calculate the torque, and we need to know that positive torques are counterclockwise, negative torques are clockwise. Okay? And then also that if I have something that's static, the sum of the torques equals 0. Let's try this. So why don't y'all try this one, and then we'll work another one. Actually, no, let's go to the homework. I'm going to work a homework problem here in class. Don't usually do that, but it's... This is on page 173. Here, I just want to calculate the net torque on this object, and notice that it can rotate about different axes. We'll just work part A, where it says it's rotating about this axis. And I want to calculate the net torque. Now, recall that torque is equal to Fr sine theta. Clockwise torques, or counterclockwise torques, are positive, and clockwise torques are negative. I'm rotating about the axis here, and so I have 3 forces that are acting on this object. How many of those forces are actually providing a torque? 2, 1, 2, or 3 of those forces are actually providing a torque. Okay, one of these forces is not providing a torque. Which one is that? The 30, the 25, or the 10? Which one? Have y'all ever opened a door? Have you opened? I'm sorry, I'm not trying to get you. But you have opened doors, right? Like if you open a door, the axis of rotation is at the hinge, right? The hinge is right here. Now, the best way to open a door, I've done this for a long time, opening doors. The best way to open a door is to come all the way over here and to push with a force that's perpendicular to the door. Because I get maximum torque if I do that. If I push as far away from the axis of rotation. But you know what's a terrible way to try to open a door? To push it over here. Now, I've been working out, so if I push too hard, I'll just knock it off. But, so I won't do that here. But you realize that if I apply a force down here, what's the torque that I'm applying to it? Yeah, no torque, basically, because my axis of rotation is 0. So which of these has an axis of rotation of 0? The 30 Newton force, the 25 Newton force, or the 10 Newton force? No, I'm rotating about this axis O. Which of those has an axis of rotation of 0? Look, we'll try it as a clicker question. I want to see what y'all. What I'm asking is, which of these forces provides 0 torque?
And what we rotating the axis of?
Just a second, I'll say it again. So the 30, the 25, or the 10. Which of these forces provides 0 torque? They give no torque at all. So it's like pushing on the hinge over there. Is it the 30 Newton force, the 25 Newton force, or the 10 Newton force? And we're rotating about the point O. Which of those forces provides 0 torque? All right, just a few more seconds. Okay, we'll stop at 25. Just guess if you're not sure. 25. Okay, good. A is the right answer. Because of my axis of rotation here, the distance from where the force is applied to the axis of rotation is 0. So this force provides no torque at all. Now the other forces provide either a positive or a negative torque. This is kind of tricky, and students sometimes have difficulty with this. But I like to imagine, I like to put my pen on the paper. I don't know, pen. Anyway, imagine that my arm is a pen. Put my pen on the paper and know that it can rotate now about this axis. So if I pull up in this direction with this force, is that clockwise or counterclockwise motion? That's counterclockwise. So this force does positive or negative torque? This force does positive torque. This force, if I pull down in this direction, that's clockwise or counterclockwise? Right. All right, so I have a positive torque here because it's counterclockwise, and a negative torque here because it's clockwise. It doesn't matter that the forces are slightly off axis. They're still going to provide this clockwise and counterclockwise forces, or torques. What if I had a force that was in that direction? What kind of torque would that one provide? 0 torque, right. So that would be sort of like, can't do it, but imagine just pushing on a door along the long axis or pulling on the long axis of the door. It's not going to do anything to the door. All right, so that force would provide 0 torque. Now, if we want to calculate the net torque for part A, the sum of all the torques is going to be 25 newtons times 2 meters. 2 meters is this value. It is R for that 25 Newton force times the sine of, and actually, I meant actually to do my angle here. So I'm going to do it there. And that'll be the way it'll be on the exam. Whatever angle you have will be the angle that you use. Times the sine of 60 plus the other torque, which is going to be negative 10. Negative because this is a negative torque here. Times what distance? 4 meters. 4 meters because that's this distance, which is R for the 10 Newton force, times the sine of 20. And then that gives us the net torque, whatever that is. I don't know what that is. You just have to be careful with a couple things. Make sure that you realize which force does no torque, because it may very well be that one of the forces you just won't consider. Well, I had intended actually to make this 60. He asked why I used 60 instead of 30. On the exam, your angle will be the angle that you use. So the angle between F and R is going to be F is in this direction and R is in this direction. And here I measured it off of the perpendicular. So that's not really usually the way that we do it. Okay? As far as you're concerned, you can just use the angle that's given. Does that answer your question, William? Okay, good. So you have to go through a couple of things. First, figure out which force provides no torque, and likely one or more of the forces will provide no torque, either because it's acting at the axis of rotation, or if I have a force like I drew up here earlier that was along the moment arm, then that's not going to provide a torque. And then figure out which torques are positive and which are negative. If they're clockwise, they're negative. If they're counterclockwise, they're positive. And then you add up the torques like this. Anybody get a value on this?
It should be roughly 30 for this 29.62.
Is it 30? Yeah? Okay, so that's 30 Newton meters. And it's positive. That means it's going to be in the counterclockwise direction. All right, let's try that clicker question back in the back and see how y'all do. Okay, so in this question, we're rotating about the point C right here. And there are several forces acting on this bar. I want to know what is the net torque acting upon it. Asking me, bro, if you're not certain. You want to figure out which forces provide torques. Are they positive or negative? Counterclockwise or clockwise? And then calculate the torques using the appropriate angle. And again, here, I'm sorry, but this should be 60 degrees from the horizontal. Get the angle. I changed the angle here. I just gave you the angle from the horizontal. You'll have 2 to 3 questions on the test, probably 2. One of them will be like this. I'll give you a bar, it'll have 3 forces acting on it, and I'll ask you to find the net force. Something very similar to this. The numbers are different, of course, but very similar. All right, let's do about 15 more seconds. Let's shoot for 2:45. Just 10 more seconds. If you're not sure. 2:45. Okay, very good. So you'll have a question like this on the test. It'll be very, very similar, just different numbers. I know that we haven't been on Chapter 8 for very long, so I'm going to tread very lightly on the questions that I give you. I want you to know how to calculate the net torque. Something very similar to this, a bar with 3 forces acting on it, and determine what is the net torque. Let's work through this. Oh, do you know where you go if you want to have your, like your whale, like I don't know, whatever kind of whale you have, if you want to have it weighed? To the whale weigh station. Okay, so we're rotating about this point. That means that which force is going to provide no torque? The 30 Newton force. I'm just going to get rid of that. I'm not going to worry about it. The 25 Newton force provides, this force provides a torque or causes motion in this direction, which is counterclockwise. So this is going to be a positive torque, and then this will be a negative torque. I'll call this torque 1, torque 2. So the net torque will equal to torque 1 minus torque 2, which is going to be 25 newtons times the distance from here to here times 2 meters times sine of 45, and then minus this force, which is 20 newtons, times this distance, which is 2 meters. Here the r is the same, but it doesn't have to be, times the sine of 20. Well, that was equal to, which one was it? C was the right answer. All right, so that comes out to positive 22. It's in Newton meters. Because it's positive, that means it's counterclockwise. So that's your last step. It could be that on this 22 Newton meters clockwise and counterclockwise, and you'd have to differentiate between the two. Yeah, China. Okay, so this force has no torque because it's acting at the axis of rotation. There are two ways that a force can have no torque. Either one, you can push at the axis of rotation, so like trying to open the door here, right? And you're never going to open the door this way. Or, if I apply a force in this direction, y'all see that? Where I apply a force along the axis of the door. So I apply a force, this is my door, along it. So then my angle is 0, and the sine of 0 is 0. They have the same r just because right now, because our axis of rotation is switched. They don't have to have the same r. R is the distance from the axis of rotation to where the force is applied. And in this case, that r was, is that it? Yeah, on the previous one in the homework, we had a different r. You want to look for the distance from the axis of rotation to where the force is applied. Good? All right. You shall have a question like this. The other type of question will be something similar to the next example, or which is a lot like what you did in lab. All right, let's try this next clicker question now. All right, so Chad, hey, that's me. Did y'all know that was my name? Actually, my name is Chadwick. My parents, they gave us all very aristocratic sounding names. Chadwick and Joseph and Anthony, even though we just go by Chad, Joey, and Tony, because we're not really aristocrats, you know. We're sort of lower middle income folks from rural Mississippi. Let's try this one. I stand 4 meters from the pivot point, so the distance from here to here is 4 meters. My mass is 75 kilograms. Kaisa, y'all know who that is? That's my wife. She has a mass of 60 kilograms. Where can she stand to balance the board? Does she stand down here, 1 meter to the left of the pivot point? Does she stand over here, or half a meter to the left of the pivot point? Or can she not balance the board at all? All right, we'll do about 15 more seconds. Let's go to, we'll go to 110, 110. Okay, good. D is the right answer. There's no place for her to balance the board. Now, let's work a problem where we actually calculate this. There's an example on the next page. Now, if you didn't get this one, hopefully after this example, I think it'll make more sense. This is a lot like what y'all did in lab. In fact, it's basically identical to what y'all did in lab. So here I have a seesaw. You ever play on a seesaw? Like if you have a kid that you're seesawing with, you put the kid on the end, and where do you sit? Maybe in Mississippi, that's how it's but around here, you put the kid on the end, and then you sit halfway, right? It's easier because it balances it out, and the kid's not up like this all the time. And so here we have a similar thing. We have a kid here that has a mass of 50 kilograms, and then I want to sit somewhere on the other side with a mass of 100 kilograms. Where do I sit to balance this? So the way we approach this is we say that the sum of the torques has to equal to 0. So I'll call this torque 1 and this torque 2. Torque 1 is counterclockwise, so it's positive, and torque 2 is clockwise, so it's negative. When I say it's clockwise, what I mean is if there are no other forces, this force would cause this thing to move in a clockwise direction. So the sum of the torques will be torque 1 minus torque 2. That will equal to 0. Because it's equal to 0, torque 1 has to equal to torque 2. And then you set those two torques equal to one another. I say that torque 1 is Fw1 times R1, and torque 2 is Fw2 times R2. I can put in my values now of 100 kilograms times G times 2 meters. This is R1 up here. R1. And then Fw2, oh, I'm sorry, that should be what? It should be 50 kilograms. Sorry about that. 50 kilograms. Fw2 then is 100 kilograms times G times X, which is our distance. Notice that the G's cancel out, and I can solve for X. So I get X is equal to 100 divided by 100, which is 1 meter. This will be the other type of problem that you'll have. So you have one problem where you have to find the net torque, and then one problem where you have to figure out which force will balance the system. This is just like what you did in math, exactly like that. You set the torques on one side equal to the torques on the other side. Yeah, David? Sure thing. Yeah, you could say he weighs double, so his moment arm has to be half. Yeah. But it might not even always be such an easy relationship, right? Might not be a whole number. Y'all can do those two questions on the test? We're going to use those more as we come back next week after the test, but that's good for this test, I think. Okay, let's do a few clicker questions. So 2 to 3 questions, one calculating the net torque, one calculating the force or the mass to balance the system, and then maybe a conceptual question, something like the next few questions that we have. We're just going to do a few. Here I want you to rank the torques from biggest to smallest. It says rank how easy or difficult it is to hold the meter stick level, but really you're ranking the torques. So you're ranking which of these has the biggest torque down to which has the smallest torque. And notice some of them might have the same torque, in fact. Is this in the back?
It's not the first question.
Oh, it's not the first one. I might have reordered it. Doing pretty well. Only about 8 of you have the wrong answer. So ask around if you're not certain, and ask to see what your neighbor has. All right, we're going to stop in about 10 seconds. Stop at 140. Look, you can make pretty short change of this if you just realize that this one and this one are equal. I have half the mass at twice the distance compared to this one. So the torque of this one is equal to the torque of this one. And when you realize that, E is the only possible option, because none of the others have A equal to B. But I can just sort of do a calculation, just taking the mass times the distance. That's not really the torque, but it tells us the relative values of the torque. So if I do 500 times 1, that's 500. 1,000 times a half, that's also 500. This is 1,000 times 1, so it's 1,000. And here I have 2 torques. Y'all did this in lab, and we won't see this on this exam, but we will see it on exam 4, where I have 500 times a half, that's 250, plus 500 times 1, that's 500. So I have C, and then D, and then A and B are equal. Okay, here you have forces that are acting on an object that rotates about the black dot. Rank from largest to smallest the torques. Look for torques that will be equal, torques that will be 0. Try to figure out which is your maximum torque. All right, let's stop at 140. 140. Just guess if you're not certain. Okay, that's right. So you could see that, or you might be able to recognize that A and D have the same torque. Because here I have 2 newtons, let's call this 1 meter. 2 newtons acting at 1 meter, that would be 2 newton meters. And here I have 4 newtons acting at a half a meter. That would also be 2 newton meters. So those 2 torques are equal, A and D. C has what torque? 0, right? This is another way to have 0 torque. You can either apply a force at the axis of rotation, or you can apply a force along the moment arm, where theta would equal to 0 or 180. So that has 0 torque. 0. This has, if I say 2 newtons times 1 meter, 2 newton meters. This would also have 2 newton meters. I'm just assuming the length is 1 meter. Here I would have 1 newton meter, 2 times 0.5. And then we have to figure out, what do I do with this angle 45 degrees? Well, this torque would be 4 newtons times 1 meter times the sine of 45. And the sine of 45 is 0.7-ish, 0.71, I think. So that is more than 2. So we're going to have E followed by A and D, followed by B, and then C has 0 torque. Let's try another one. A is the right answer there. A rigid body is in equilibrium if which of these? The net force is equal to 0. The net torque is equal to 0. Neither of those, either one of those, or both of those must be true for a rigid body to be in equilibrium. They're doing well, mostly. We'll stop at 40 seconds. 40 seconds. Okay, good. E is the right answer. You have to have your net force is equal to 0. That's like from chapter 4. And then also our net torque has to equal 0 as well. I think that's the last one we're going to do. Let's see. Yeah. All right. Let me recap what we're going to have on this exam. I'm not sure. There should be an empty page at the end of your chapter if you want it right there on the previous chapter maybe. So we got chapter 5, 6, and 7. Listen, we'll have a review session in class on Monday, and then we'll have another review session on Tuesday around noon or 1 or so. I have to check the class schedule. But I'm just sort of giving you an overview of what to expect for the test, sort of all the topics that we've covered. So in chapter 5, we had work and energy. You need to be able to calculate the work done by a force, need to be able to determine how much work, be able to rank the work that's done in particular scenarios. We've done some questions like that. Energy, you need to have a couple things here. The work energy theorem, that is, if I do work on an object, I increase its energy. And so if I do work on an object, I make it move at a certain speed, or I change its position with regards to the Earth. We had some questions like that where you have to calculate the work and then set that equal to the energy. And then also, of course, our conservation of energy. That's like, our roller coaster problems. Are our spring problems. You can see either or both of those. Likely you'll see both. That you'll see springs and gravitational energy for conservation. We had Hooke's law as well. That was sort of an aside. Probably not going to see Hooke's law, but don't be thrown off if you do see it. The equation, is the equation on your equation sheet? It is, okay, for Hooke's law. You will have that equation sheet, the one that's in the back of your book, and the one that's on the website. I think that's it for chapter 5. Oh, and then there's also power. Power is work over time. It'll be like some of the problems we worked in class. I'll give you the work or the energy expended and the time, and then you have to calculate the power. Or you might not see that at all, I'm not sure. Chapter 6 was momentum. So we have two types of problems for momentum. You have the F equals delta P over delta T, and then you have collisions. Collisions is where you say PI equals PF. You need to know the different types of collisions as well. What's an elastic collision? What defines that? What's an inelastic collision? Elastic energy is conserved. Inelastic energy is not conserved. Only momentum. I think that's it for chapter 6. Yeah, there wasn't that much in chapter 6. And then in chapter 7, you need to know your kinematics. Listen, there's at least one homework problem where you have to do substitution, where you have two equations and two unknowns. You will not see that on the exam. But all the other homework questions are good. I mean, that question was good. I think it was the drill, the dentist drill. It's a good question. It's just you're not going to see that level of algebra on the exam. It just takes too long to work those. But you need to know how to do your kinematics. You need to know how to convert angular to linear quantities. that's that S equals theta R, etc. V equals omega R, A equals alpha R. And you need to know your centripetal forces. How to figure out what is the centripetal force. The centripetal force is the force that causes circular motion. So we talked about 3 different examples, like the tension in the string, the normal force on that thing that spins around at the fair, and the friction on the tires. You had some homework problems dealing with at least a couple of those. So take a look at those. And that's it for Chapter 7. And then Chapter 8, you'll have 2 to 3 problems. You will have one that is net torque, just like we did with the bar and the 3 forces. You have 2 with equilibrium. The sum of the torques equals 0. I have this, I have a mass over here. What mass goes over here to balance it? And then a third, like the concept test questions that we had, probably is going to be like those ranking questions that we had, ranking the torques. I did pretty well on those. And then that's what you need to be studying between now and Wednesday. Any questions? It'll be a similar format on the exam, 26-ish questions. All right? All right, have a good day, okay? See you next week on Monday. We'll do a review in class.